Hello everyone, this is Pallavi Nagulapally, working as an assistant professor in EC department, Marri Reddy Institute of Technology and Management. Today I'm going to talk about architecture of 8086 microprocessor. Architecture of 8086 microprocessor is a very first microprocessor introduced by the Intel company in 1978. And this microprocessor is very well known for its pipelining architecture. 8086 microprocessor is a two-stage pipeline microprocessor with 16-bit data bus, 20-bit address bus, and 1-bit control pin. So whatever you're looking at right now is architecture of 8086 microprocessor. As you can see, it is divided into two sections. One is BIU unit and EU unit. Before going into the sections, registers, where the fetching, decoding, and execution happens in the architecture, we're supposed to know why an architecture has a pipelining in it. Before introducing 8086 microprocessor, we used to work with the 8085 microprocessor, which is an 8-bit microprocessor with 8-bit data bus, 16-bit address bus. What is the problem here with the 8085 microprocessor is we don't have any sections in the architecture. Because of this, there is a delay in processing the instructions written to the 8085 microprocessor. What kind of delays? We have to wait till the first instruction being executed completely, then the second instruction will be fetched, decoded, and executed. As we all know that if you want to execute any program, any instruction in the program, it has to go through 3 stages: fetching, decoding, and execution. So by looking at this problem in 8085, what the Intel people thought that can we divide the architecture into sections so that we can reduce the time delays in processing. Because of this idea, we have an sections in the 8086 microprocessor. It is a 2-stage pipeline architecture, as I said before. There are BIU unit and EU unit where all kind of operations happen. In the BIU unit, we are seeing the fetching where all the instruction is being fetched into the architecture from the memory unit. And here the control unit, what you're looking at right now, is used for decoding and also sending the command signals, control signals to all over remaining parts of the architecture. And in the EU unit, we can see the execution happens. Let us start how the fetching, decoding, and execution of any instruction happens inside the architecture of 8086. The very first thing starts from calculating the physical address. What is a physical address? It is an unique address given by the memory unit where the data is being fetched, where the data is being stored. So first we need to calculate the physical address where the instruction is being saved. Then we can do the rest of the operations like by decoding and execution on that. The fetching part will happen from the memory unit, which is a separate entity which is present outside the architecture where all kind of data is being saved. And 8086 is capable of working with 1 MB memory, means 1 million locations. We can save the data in 1 million locations. Each location will have up to 1 byte of data in it. So how we can calculate the physical address which into the architecture so that we can fetch the data? Here what happens, you can see in the memory we are having segments. In the 8086, we have a memory, a capacity 1 MB, and this 1 MB memory is divided into 4 sections, 4 segments. We are having code segment, stack segment, data segment, and extra segment, where the data is being saved, and each and every segments have addresses. And we are calling those addresses as physical address. And these physical addresses have data in it, and those data is being fetched into the architecture by calculating the physical address of it. And to do that, we require 2 things. One is segment address, one is offset address. Segment address will be stored in the segment registers. Whatever you're looking at, the rectangular boxes in the BIU unit and the EU unit are called the registers here. And we supposed to talk about these registers. Registers are just used for saving the data. You can save the data in it. We can save the address in it. So we are having 14 types of 14 registers here. And we are having registers for saving the segment addresses, and we are having registers for saving the offset addresses. Two kinds of registers we have, which are absolutely used for saving the addresses. One for saving the segment address, second for saving the offset addresses. And if to calculate the physical address, we require both. And you can see whatever formula you're looking at right now here, which will be used for calculating the physical address of any data which you want to be getting, which you want to access and do the rest of the operations on that. So physical address is a combination of segment address into 10H plus offset address. These addresses was stored in these registers, segment registers and offset registers. We are having 4 types of segment registers: code segment, data segment, extra segment, and stack segment. And those addresses, the very first addresses of those segments were saved in these 16-bit registers. Yes. And these offset addresses will be stored in this rest of the 5, what you're looking at: IP, SP, BP, SI, and DI. These are called the offset addresses, where the offset addresses of these segments have been saved. And for example, just imagine I want to access an data which is stored in the code segment. And if to do that, I have to first calculate the physical address. And physical addresses is a combination of segment address and offset address. And as we all know that in the code segment, the offset addresses were pointed out by instruction pointer, IP. And these two, if you want to fetch the data which is stored in the code segment, will be taken first by calculating the address of segment address and the offset address, which we are calling as physical address here. And segment address will be taken from the code segment register. Offset address will be taken from the IP instruction pointer. Both will be given to this unit which you are looking at, just be similar to the ALU here. And this unit will do the calculation. And after that, after doing the calculation, that physical address will point it out again to the memory unit where the data is being saved, which is a separate entity outside the architecture unit. And the data is being moved, after calculating the physical address, the data is being moved into the prefetch queue. It is a 6-byte prefetch queue, which is working in first in, first out logic. Here in the prefetch queue, the data is fetched, which is fetched from the memory unit after calculating the physical address, will be moved into this prefetch queue. It is a 6-byte prefetch queue. Each and every location have 1 byte data in it. Like that, we have 6 locations. In these 6 locations, we can save the data. And here, the logic applied is FIFO, first in, first out. Where the fetching part, after the fetching part, in this prefetch queue, the fetching part is done. After that, once the fetching of the instruction is done into the architecture, the second thing applied is decoding. Here, fetching is nothing but we are considering the data which is stored in the memory, which is in a separate entity, into the architecture. This process is called fetching, and we are saving them first initially in the prefetch queue. It is a register, 6-byte register. It's a queue. And after that, once the data is being fetched, it will be decoded in the control unit, where the data is being understood what we have to do with it. After decoding, the control unit will send signals to all the module in the architecture that some certain data is being fetched into the system, and this is what you have to do with the data, and arrange yourself accordingly. This is what the control unit will do. Give the command signals to all the remaining parts of the architecture. Once the decoding is done, it is moved into the second stage of the architecture, which is EU, execution unit, where all kind of execution is happening. The data which is been decoded initially will be moved to these 4 registers, which you are looking at here, which is also called as general purpose registers, which is of size 16-bit each. We can use them as 16-bit. Otherwise, you can use them as 1 byte, 8 bits, based on the requirement. And initially, it was moved into the general purpose register, which the data which is being decoded. Then it is moved to the ALU unit for the further processing, where the execution will happen. ALU will do all kind of arithmetic and logical operations. Once the execution is done, again the data is moved into the general purpose registers. This is how the operation is done. Only thing we have to remember here is, at the end of the day, it is an instruction. No matter what language you are working with, high level, assembly level, everything will go through 3 stages: fetching, decoding, and execution. Here, fetching part is done in this unit, BIU unit, by calculating the physical address, and decoding of the instruction which is being fetched will be happening in the control unit. After decoding, it will send the signals to all the remaining parts of the architecture, what we have to do with the data which has been fetched into it. Then in the second unit, which is EU unit, with the after decoding, the data is temporarily moved into general purpose registers. Then again, after temporarily movement into general purpose register, the data is again moved into the ALU for the further process, for the execution, actual process, the execution. Once the execution is done, the data is being moved again into general purpose registers. So these general purpose registers are user-friendly registers given to the programmers. You can use them, enable them how many times you want while through the execution process. And here, the operand register, it is also a register, and the flag register. These two are also a part of the architecture. What happens here is, while writing the program, in the assembly language, while writing the program, we work with the registers, we work with the keywords which are predefined. And if you convert them into the binary sequence, if the instruction is completely written by the user, defined by the syntaxes, counter syntax, without any user-defined data is there. If the instruction is in that form, that's complete sequence, the binary complete sequence is called opcode. And if the instruction is having a user-defined data in it, of course, it will be in the binary form, but that sequence will be called as an operand. For example, if I am writing an instruction like this, and the second I am writing like this, so both are instructions, both are called an instruction, both are doing the same process. The first instruction, I am trying to move the data which is stored in the BX register, 16-bit data, into the AX. And here also I am doing the same. Instead of moving between the registers, I am giving the data directly in the instruction. And after that, I am trying to move into the AX register. So this instruction, what you're looking at, is a variables defined already. This is not a user-defined one. So this complete sequence will be called as an opcode. And this sequence, in this, we are having a already defined one and the user-defined one. So this code will be called as an opcode, and this will be 2345H, whatever value which is user-defined will be called as an operand. And this sequence, if the instruction is written like that, that sequence will be saved in this register operand temporarily after moving in here. And it will again move into the ALU for the further process, for the movement process. And like that, the operation happens here. It is all 16-bit. And the last register in the architecture is flag register, which is a status register. Just imagine we are doing the arithmetic operations, all kind of arithmetic. All the 4 operations applied at a time in the 8086 architecture. There is a very good chance of generating a carry bit, auxiliary carry. While doing the subtraction operation, there is a very good chance of generating the borrow. If the MSB bit is 1, we can indicate it by as a sign bit. So status, after execution, while execution. If you want to see the status of the process of the instruction, where it been, how it been, and what happened after the execution, what is the status of it, that will be indicated by this flag register. So this is all about the architecture of 8086. At the end, we need to understand that 8086 is a two-stage pipeline architecture with 16-bit data bus, 20-bit address bus, and 1-bit control pin. Initially, the data is stored in the memory unit. After that, the data is moved into the architecture by calculating the physical address. Physical address required two things, segment address and offset address. Both was present in the memory unit, and those two addresses were saved inside the architecture. In the segment addresses was saved in these 4 registers, CS, SS, DS, and ES. Offset addresses was saved in these 5 registers, IP, SP, BP, SI, and DI. And if you want to access any data which is saved in the memory unit, first we have to start by calculating the physical address of it. And if you want to do that, we require two things, segment address and offset address. For example, let us take an data which is saved in the core segment. And if you want to get access to one of the location, we require two things, segment address of the core segment, the starting address location, and the actual location of the data which is stored, which is we're calling it as an offset address. Both will be moved into this unit where the calculation is done, pointed out to the memory, and the data is being fetched into the prefetch queue, which is working with the logic FIFO, first in, first out. Once the fetching is done, the data is moved in the control unit where the decoding part is occurred. And also the signals, what we have to do, the command signal, the control signals will be moved to all the units of in the architecture. Once the decoding is done, the final stage was the execution, implementing. That is done in the EU unit, execution unit. But the data which is decoded initially moved into the general purpose registers, one of the general purpose registers. And after that, it was moved into the ALU for the further process, for the actual execution process. If the instruction is completely defined like this, the sequence is called as opcode if the instruction is having and user-defined data. The partial of it will be called an opcode, and the remaining part, the user-defined one, will be called as an operand. That data is stored in this operand register, and it is moved into the ALU again, and the execution happens here according to the instruction. And again, after execution, the data is moved again into the general purpose registers, which is a user-defined one. And the flag register will tell the status of the instruction while and after the execution process, where what happens to the instruction which we have written, the status of it. That will be indicated by this flag register, which is also a 16-bit register. Hope this topic is clear. Thank you for today. We will meet in the next topic in the memory segmentation. We will talk about the memory segmentation, this entity, what you're looking at right now here. What is the memory, what is the size of the memory 8086 can work with. All these things we can see in the next lecture, memory segmentation. Thank you.